So chapter 16 is acid-base titration and pH. There are two parts to this chapter, the first of which is quite lengthy, so there will be multiple videos for sure. The second part's much shorter. So first off, just a little bit of a review. So what is the hydronium and hydroxide ions? You should already know both of these and be familiar with them from chapter 15. So just recall that acids always begin with H, hydrogen, and they donate protons, that H+. That is our Bronsted-Lowry definition of an acid. Bases, on the other hand, end in OH, and they accept protons, which is, once again, the Bronsted-Lowry definition of a base. So once again, what is a proton? A little bit confusing because it's not the same thing you thought of in Chemistry 1, where you were thinking of specifically a subatomic particle. This is really just a nickname, and you'll see why in a minute. So a proton in this sense is basically a hydrogen ion, H+. So if you look at this depiction of hydrogen, hydrogen has its nucleus, and in its nucleus, it only has one proton. There are no neutrons. And hydrogen also only has one electron. So when you take hydrogen and make a cation out of it, meaning you take an electron, it becomes more positive. And if you take this electron away, what is left? Only the proton. So that's why it gets that nickname as proton. So once you have this H+ ion, it's going to attach to water if water is present, and that is how you form the hydronium ion H3O+. So the hydronium ion is acid-based. The hydroxide ion is attached to all the bases already, OH-. So acid-base reactions, we briefly talked about neutralization reactions, and that's when you're going to have an acid reacting with a base. You get two products, generally water and some type of salt. A salt being a metal from the base, the cation, and a non-metal from the acid, which is an anion. So the negative anion and the positive cation, opposites attract, they come together, and you get a salt. So just to remind you of a common example of a neutralization acid-base reaction, we have HCl, hydrogen chloride, or now you know it as hydrochloric acid, and sodium hydroxide, which is our base. So basically what happens is, if you break these apart into ions, you get H+, L-, Na+, and OH-. Okay, well, the H+ and the OH-, opposites attract, come together to form water. It's no longer charged, they're no longer ions. Plus and minus came together. You're left with this negative anion from the acid and this positive cation on the base. Once again, opposites attract. The positive ion comes first, so we get NaCl, and that is table salt. So these neutralization reactions, you have an acid and a base, you form water and some type of salt. So next we need to talk about the self-ionization of water. So water can ionize with itself. I don't know why this word under is here. I apologize for that. Okay, so for the example, we have water plus water, and we're getting a hydronium ion and a hydroxide ion. So let's see how that happens. So basically, if we break this apart, we have H OH, and H, OH. Well, one of the H's attaches to the water. So now we have 1, 2, 3 hydrogen, 1 oxygen still. And that leaves us with OH minus. So when water self-ionizes, you get the hydronium ion and hydroxide ion as your products. So concentrations, which can also be written as brackets. So these square brackets mean concentration at 25 degrees Celsius, because that's room temperature, are equivalent to each other. So at room temperature, the hydronium ion's concentration, which is represented by this, is equivalent to the hydroxide ion's concentration. Both of those being 1 times 10 to the negative 7 capital M, which is molarity, or molar concentration. So looking at the ionization constant for water, which is abbreviated capital K, lowercase w, and the W is a subscript. The equation for that is equivalent to the hydronium ion concentration, H3O plus in brackets, multiplied by the hydroxide concentration, OH minus in brackets. So Kw for water equals 1 times 10 to the negative 14th capital M squared. And how do we get that? We took the value of hydronium ion concentration at room temperature, 1 times 10 to the negative 7th M, and we multiplied it by the hydronium ion concentration on the left. So 1 times 10 to the negative 7th multiplied by 1 times 10 to the negative 7th gives us 1 times 10 to the negative 14th M squared, because we multiplied the units together. So the ionization of water will increase as temperature increases. With that being said, the ionization constant will also increase. So just looking at this chart, you don't need to memorize it. Like I said, we're using 25 degrees Celsius because that's room temp. At 0 degrees Celsius, you got this value, negative 15, meaning smaller. At 10 degrees Celsius, we've slightly increased, a bigger number. 25 degrees Celsius, room temperature, an even larger number. And at 50 degrees Celsius, an even larger number. So the ionization will increase as temperature increases in water. We do assume, however, once again, that our Kw is within normal room temperature ranges, which on average is 22 to 27 degrees Celsius. It's easier just to say 25. So actually looking at some problems. Using this equation, our ionization constant for water, where the hydronium ion concentration is equivalent to the hydroxide ion concentration. So in this case, it says given a 1 times 10 to the negative 4th molar solution of HNO3, find both the hydronium and the hydroxide concentrations. Well, the first thing you have to look at is, what is this substance? Is it an acid or a base? And hopefully you're aware that it is an acid. And now that you know how to name these, hopefully you specifically know it's nitric acid. Okay, so here's the cool thing about these problems. If this is an acid, its concentration, represented by M, is actually equivalent to the hydronium ion concentration. So H3O plus is equal to the concentration because it's an acid. Okay, we just have to find hydroxide concentration. Well, we're going to use this equation, and we're going to rearrange it to solve for OH minus. So Kw equals hydronium ion concentration times hydroxide ion concentration. I want to get hydroxide by itself. I'm going to divide both sides by the hydronium ion. And that means that Kw divided by the hydroxide ion concentration equals, let me go back. Kw divided by the hydronium ion concentration is equivalent to the hydroxide ion concentration. So this is the equation we need to use. Okay, so let me erase this, clean it up for you, and then we'll continue. So once again, we're looking for the hydronium ion concentration. That is going to be equal to Kw divided by the hydronium ion concentration. What is Kw? That was on the last slide. 1 times 10 to the, do you remember? Negative 14 m squared. So that's Kw, always it's a constant, divided by our hydroxide concentration. 1 times 10 to the negative 4 m. So plug that in your calculator. 1 times 10 to the negative 14th divided by 1 times 10 to the negative 4th, and you get 1 times 10 to the negative 10 molar as our hydroxide ion concentration. And you can always go back and check this. If you multiply these two together, you should get Kw. Okay, let's try another one. Given a 1.6 times 10 to the negative 3 molar hydrochloric acid solution, find the hydronium and the hydroxide concentrations. So once again, the first thing you have to do is start with your substance. Is this an acid or a base? It starts with an H, so it's an acid. Specifically, hydrochloric acid. Once again, if it's an acid, the concentration, the molarity, equals the hydronium ion. That's a given, we already know that. In these problems, you have to know one or the other. We also know that Kw is equal to 1 times 10 to the negative 14th. So once again, to find our hydroxide ion, we take Kw, we divide by the hydronium ion. So 1 times 10 to the negative 14th divided by 1.6 times 10 to the negative 3. So plug that in your calculator, and you get 6.25. 2 decimals is good, times 10 to the negative 12th with our unit capital M. If you didn't get that, I would guess you probably put it in your calculator wrong. And you can check your work by multiplying these two together, and you should get the Kw constant, or very close to that. All right, try another. Given 3.45 times 10 to the negative 2 molar NaOH solution, find hydronium and hydroxide. So first identify it as an acid or base, and then do the algebra. So pause the video, try it out. Okay, in this case, we have NaOH, which is a base, sodium hydroxide. So now our concentration is equivalent to OH minus. So now we know OH minus 3.45 times 10 to the negative 2 m. We want to find hydroxide. Once again, we know Kw. So in this case, we want to find H3O plus. So we're going to divide Kw by OH minus. So Kw, 1 10 to the negative 14th, divided by our OH, 3.45 times 10 to the negative 2 m. Don't forget units. Plug that into your calculator. And like I said, if you're struggling with plugging into your calculator, please reach out to me. Sometimes using the EE button, if you have that on your calculator, is better. So you would type in your calculator 1 EE negative 14 divided by 3.45 EE negative 2. EE takes the place of times 10. So sometimes it's just easier. So plugging that in your calculator, you get the hydronium ion concentration is about 2.89, 2 decimals times 10, then negative 13. Once again, you can check, multiply those together. You should get close to the Kw value. All right, one more, try this one. Pause the video, work it out, check your answer. So hopefully you've tried this. So NaOH is our base, sodium hydroxide again. So this molarity concentration is equivalent to the OH minus, which I've written here. To find the hydronium ion concentration, I take Kw's constant value divided by my OH concentration. Don't forget units. And I get that my hydronium ion concentration is about 1.06 times 10 to the negative 11. Okay, last one. Try it out. So hopefully you realized NaOH is our base. So 4.4 times 10 to the negative 6 m is going to be the molarity and equivalent to the OH minus concentration. Finding the hydronium, I take my Kw value divided by my OH minus concentration value, and I get a number of 2 times 10 to the negative 9. So once again, if you're struggling with getting the values from your calculator, please reach out to me and I can show you through Zoom specifically what to do or what you're doing wrong potentially. Okay, so now that we know how to find the hydronium and hydroxide concentrations, can we actually verify if it makes sense for an acid, a base, or a neutral solution, whatever we're talking about? So in a neutral solution, the hydronium and hydroxide ion concentrations are equivalent or very close to equivalent. In an acidic solution, this should make sense, the hydronium ion concentration is greater than the hydroxide because hydronium ions, that H gives us acids their properties. In a basic solution, the hydroxide ion concentration is greater. Once again, that should make sense for a basic solution. So now we're just going to go back to our previous examples and verify. So you're just double checking. You do need to know how to do this. Okay, so going back to example 1, we said that our hydronium ion concentration was 1 times 10 to the negative 4, and hydroxide was 1 times 10 to the negative 10. Remember that the smaller the negative number, the bigger the negative number, the smaller the number is. Okay, so in this case, 1 times 10 to the negative 4 which is our hydronium, compared to our hydroxide. Which one's bigger? This one is. The smaller the negative number, the bigger it is. The bigger the negative number, the smaller it is. Okay? That matches acidic solution. What was the substance in example 1? Go back and look. It was HNO3, which is an acid. So this makes sense. So you're just verifying that your numbers and your math actually make sense. Okay, looking at number 2. Hydronium, 1.6, 10 to the negative 3. Hydroxide, 6.25 times 10 to the negative 12. Okay, which one is bigger? You can rewrite it out how I did before. In our case, which is bigger? This one. So the negative third is much bigger, closer to 1 than to the negative 12. Okay, so think of a number line. So we're saying this is an acidic solution. Go back, look at number 2. What was the substance? HCO, which is an acid. So it all makes sense. Let's verify number 3. In number 3, we had our hydronium is 2.89 times 10 to the negative 13. And our hydroxide, 3.45 times 10 to the negative 2. So that's why it's important to get these numbers right, because you're going to need to use them. Okay, so in this case, if you want to compare the numbers side by side, feel free to write them that way. Which one is bigger? It's the hydroxide. This number is much bigger. To the negative 2 is bigger than to the negative 13. So we're saying this is a basic solution. Go back in example 3. What was the substance? It was NaOH, which we know is a base, sodium hydroxide. So once again, all of our numbers match up. We're just verifying that the concept makes sense and our numbers make sense. All right, try this one by yourself. Go back to example 4. See what you get. See if it verifies. So going back to example 4, I have my hydronium versus my hydroxide ion concentrations. In this case, the hydronium ion is bigger. It's a less negative number, if you will. So we're going to say it's a basic solution. What was my substance? It was NaOH, sodium hydroxide, which is a base. So everything makes sense. Okay, last one. Try this one. Okay, so here are my hydronium and my hydroxide ion concentrations. To the negative 9 to the negative 6. Hydroxide is bigger, so we think it's a basic solution. Going back and looking at the substance, NaOH, it is basic. So we have verified that our concept, our numbers, our understanding makes sense.